All right, in this video, I'm going to show you how to solve problem number 3 in version C of our practice final exam. So we have a U.S. Postal Service will not accept a box for domestic shipment, I guess only if the length and girth, right, so the sum of these two values, and girth is the distance around the box, does not exceed 108 inches. So what dimensions we'll give it a box with a square end and the largest possible volume. And right there, those are the key words here, largest possible volume. That means that we're in an optimization sort of setting, right? We want to maximize volume. So this indicates, right, we're doing an optimization problem. We want to maximize volume. Well, this is a box, so I'm going to be thinking about a volume of a box. So this is going to be maybe length times width times height. I notice it already mentioned something about length down here, and then we're going to have girth. So let's go ahead and maybe draw a picture to see the kind of situation that we're in. So in this case, if I have a nice box here, maybe it has a length, and then the distance around it is this value girth. So girth is going to be kind of this plus the bottom plus this other side. So maybe let me go ahead and draw kind of, this is the side that we can't really see here, and edges and stuff. So that's going to be my girth right there. And I guess the other big thing here is that we have the fact that this is a square end, right? So maybe in this case we have that the width is equal to the height. So right, so this would normally be maybe the width and this would be the height, but they're equal to one another. So that's a lot of information. We can actually simplify down our volume equation then to say that this is length times width, or this is going to be maybe width squared in this case. And okay, so we have some other information about this 108 inches, right? So if I sum together the length and the girth, so this is the distance around, well, this is going to be one width, another width, another width, another width, right? Because again, height is the same thing as width. So if I sum all the way around there, that's going to be 4 widths. So if I sum the length and the girth, which is again the distance around here, this is 4 widths. Think of it like a perimeter sort of deal, that it should not exceed 108 inches. Well, again, if I want to maximize my volume, let's use all 108 inches. And this gives us a way, right, to kind of reduce down our volume, which right now has 2 variables, into just 1 variable, right? Sometimes this is called a restriction equation. So let me go ahead and rearrange this. This is going to be L is equal to 108 minus 4W. And now I can go ahead and plug this in everywhere I see an L up here. So this is going to be volume is equal to 108 minus 4W times W squared. And now we have our volume equation in terms of just 1 variable. Let's go ahead and at this time think about a little, right, what are the kind of allowable values for W, right? What is the domain of this function is another way to say that. So in this case, well, does it make any sense for W to be equal to 0? Probably not, right? Or less than 0, right? Negative numbers, anything like that, that probably doesn't really make sense. And then also, well, if you don't want it to exceed 108 inches, well, that means that there's really some upper bound, right? Because, I mean, even if you have a very, very flat box, right? So the L's basically 0. If you used up all of it in these W's, right? You have 4 of them going around, you still can't exceed that 108 inches. So this puts an upper bound on it, and actually right around 27, right? So 27, right? 27 times 4, that's how I got this number, would be 8. And there'd be a 2 here. 2 times 4 would be 8, so that would be 108. So it's got to be somewhere between 0 and 27. This is kind of the allowable range for our W's. Okay, and this is great. This is going to help us determine where are we looking for critical points. Because again, we want to maximize volume, so I'm going to be taking a derivative here soon. So let's go ahead and expand this out a little bit. And right, this is going to help me. So back here, I'd have to use the product rule. If I distribute those W squareds, now I don't have to use the product rule. So I'm going to have V prime is equal to 216 W minus 12W squared. And so again, we're looking for critical points, right? Because critical points is where things minimize or maximize. So I'm wondering, when is this undefined and when is this 0? Well, it's never undefined, right? Because we don't have any division, we don't have any square roots, anything like this. So our only hope really is when this is equal to 0. And so now we have a nice quadratic, there's all sorts of ways to solving quadratics. My favorite is, of course, factoring. So I noticed, well, if I factor this, I can factor out a 12 and a w, and then in the first term, this takes a minute, but you'll see that this is equal to 18 left over. And in the second term, well, if you factored out a 12 and a w, all you'd have left over is a w. So this implies either w equals 0 or w is equal to 18. Those are our two critical points, but notice w equals 0 doesn't really make sense, right? It's not in the domain. So let's go ahead and exclude that one. So that means our only critical point is w equals 18. So that's probably our answer. That's our only really chance. But we have to prove that this actually does maximize volume. So, okay, I want to prove that this does maximize volume, so I'm going to set up a number line here on our domain, 0 to 27. I'm going to plop down 18 here, and again, we're plotting information about the derivative. So if I go ahead and choose test values, right, for instance, 1 down here, maybe 20 is a nice number up here, and if I plug those into my derivative formula, so again, maybe I go ahead and I look at this right here for my derivative. So if I plug in 1, right, this is going to give me 12 times 17. And again, the big thing here is that this is positive. So here we have a nice positive value. Now, if I plug in 20, I'm going to have 12 times 20 times 18 minus 20. So that's going to be negative 2. And so I have a positive times a negative, and the big thing here is that that's negative. So we can see that we go from increasing to decreasing. So therefore 18 actually is the maximum. So w equals 18 is a maximum. All right, couple things here. I did a bad job, right? So we have units in this case. So go back up here, right? So everything is in inches. So I want to do w equals 18 inches is a maximum. So always include your units if you can. And then the second thing I always have to check is, did I answer the question that they wanted me to answer? So back up here, it asks what dimensions will give a box of the largest possible volume. So I have the W dimension, but what should H be, right? And what should L be? So let's solve for all of the dimensions. Well, in this case, my W and my H are equal to one another. So in this case, we're going to have this is also 18 inches. And then finally, what about the length? Well, length, we can use this right here to figure out what should the correct length be. So 108 minus 4 times 18, and that's going to be 108 minus, let's see, 72, giving us a final answer of 36. And again, this is in inches. So going back down here, 36 inches. And now we have all of the dimensions, which is what it wanted. So there is the dimensions for a box with maximum volume. All right, and that's it.